All right, so this is number 33 from the optimization section 4.7. And it's like you're trying to maximize, I think, the printable area, right? Actually, no, we're trying to minimize the dimensions of the poster. We have a fixed printable area. So you could do that question either way. They can give you like margins requirements, restrictions, and they can ask you like what size, what dimensions of a poster would give you the max printable area, or they can give you like the fixed like the area of the poster itself, or they can give you the printed material requirement, and then you're trying to make the minimum amount of poster, I guess is the idea. So in this case, that's what we've got. You want the printed area. The printed area is what's fixed, right? Is 384. And so we'll note that. That's square centimeters. And it's the area of the whole paper the poster that we're trying to minimize in this case. Minimize, so this is the optimization piece. Minimize printed area, or total area. I'm struggling here. Total area. And so the total area is A equals, and length times width, right? So start there. That's our primary equation, right? That is the thing that we are trying to maximize or minimize, to optimize. So now what we want to do is, the issue is when we write that equation first, we usually have multiple variables in there. And that's what we want to fix. That's the whole point of these like secondary equations, is to substitute in and eliminate it down to one variable, basically. And it doesn't even have to be L or W. Maybe it'll end up being in terms of some other variable X or whatever. So at this point, a diagram is usually helpful. Here's my poster. And I have margins. I have margins on top and bottom of 6. And then I have side margins of 4. And again, this is all in centimeters. Just want to make sure that nobody's playing a trick on you and using different units. I'm not even going to write the units because it's all centimeters. It's fine, or square centimeters. So this is also 4. And then what we know is, trying to use a different color here, purple. We know this printed area. So that's like this middle part, right? This is 384 here. And again, that's just this part here. So that's our constraint, is that we have to have that, right? It's like, you know what has to be on the poster, so you know what size that has to be, and you know like a certain amount of text, right? And then you know the margins, but what's variable is you could make the poster wider, right? And still have those 6 inch or centimeter margins on the top and bottom, and 4 centimeter margins on the sides, or you could make it taller and skinnier. And the idea is like, if you make it really wide, you're losing, like, in order to, once this gets too narrow this way, right, then you have to make it really long to make up for it. And these don't get any narrower, right? And same thing the other way. So there's going to be a sweet spot in the middle where you've got like, the best ratio of like printed area to total area. And that's kind of what we're looking at. And it's going to be related to those margins, the 6 to the 4. Okay, you probably see it in the answer actually. So what we need to do is the total area, you just want to keep in mind, that's like the entire length and the entire width, right? And so we have to define some variables here, and you could use like L and W there. You could use X and Y. You got 2 choices here. You could either let like, X and Y be like the side and top of the whole poster, or you could do it for the printable area. Really kind of your call. I guess I would say make the secondary equation easier, because then it's easier to sub in. Does that make sense? And so if I let this be X and this be Y, like for the printable area, here, let me just get rid of that arrow I just drew, because now it's going to annoy me. So if I let this be X and this be Y, then my printed area is X times Y. But just, L and W now are not the same thing. So how do they relate? What's L in this case? Well, L is X plus 8, right? Plus 4 plus 4. So let me write that down. Equals x plus 8. And then w, or height, or base times height, I don't know, whatever, is y plus 12. Okay, and you might think, well, what did we just accomplish? We took our primary equation and we did not get rid of a variable. We only made it more complicated. And there's some truth to that. But what we accomplished too is we tied this primary equation to this secondary equation, 384 equals xy. And that's how we're going to sub in. Does that make sense? It's got to be complicated somewhere. It was either going to be here or it was going to be here, right? If I did like base and height of the whole thing, then this would be like b minus 8, and this would be like h minus 12. So one way or another, it's going to be complicated. I made the decision at the beginning here to go this way because I think now I like to sub in for y and get everything in terms of x, just like a personal, like conventional preference, I guess. So that's just 384 over x. So I'm going to say 384x to the negative 1. Cool? Setting myself up for the derivative with power rule. So I'll use the power, x to the negative 1 power instead of the ratio. And now what we can do is we can substitute this in for y. And now we have area in terms of just one variable, x. I feel like that's usually the toughest part of these problems, is getting the setup, getting it down to one variable. Once you do all that, the calculus part really isn't that bad. It's kind of funny. People talk about calculus. I feel like it's one of those things people talk about like it's so hard, and it's got this reputation among people, especially people who've never taken advanced math. Like, oh, calculus is like this big thing. And then when you actually get to calculus class, the hard part is the arithmetic and the algebra, right? And the geometry. Calculus is easy. We can get further in calculus. The calculus gets pretty funky too. Anyway, there's a of x, and we're just going to distribute here. And you could do a product rule, but I'd rather not. So the x's cancel there when I do that product. So I'm just going to get 384, and then I'm going to get a positive 12x, and then I'm going to get a 8 times 384. I'm not even going to bother multiplying that right now. 8 times 384, because maybe I'll be able to reduce stuff later anyway. So I'll just keep it separated. And then 8 times 12 is 96. So plus 96. And you could put the 384 and the 96 together, but it seems like a wasted effort, because what's about to happen to that when I take the derivative? Yep, 0. And so my derivative is just going to be 12. And then this thing, right? Bring down the negative 1. So minus 8 times 384 times x to the negative 2. And I'm going to solve that equation now equal to 0, basically. So funny story. I was recording that in class, and I guess it's not that big of a story. The microphone batteries cut out in the middle of it. Well, 2/3 of the way through. So I'm just going to really quickly kind of end the video here, but I wanted to finish it up. Yeah, we were here. We had found the derivative, and we're setting it equal to 0, right? We want to find the critical numbers of a. And so you set a prime equal to 0, or look for places where it does not exist. By the way, a prime does not exist when x equals 0, since that's a negative power. That's like an x squared on the bottom. And so, x equals 0 is a critical point, except that it's not really in the domain, because x can't equal 0, right? Like, that's not possible. If x equals 0, there is no y value that would allow that printable area to be 384, since x is the width of the printable area. So we can disregard that. And then that means the only solution we're looking for is a prime equals 0, because that's the only other possibility. And so when you set that equal to 0, kind of set it equal to 0, add this term to the other side, you get this equation. And then I just kind of multiplied both sides by x squared to move the x squared up there, divide by 12. And I covered up some of my work here so I can reveal it. Funny, this program, you need the same color rectangle. Oh, wow, you can actually see that. That's funny. All right. To remember that might be useful. Anyway, you get x equals, you can obviously use a calculator probably for something like this, but I like doing arithmetic by hand. 8/12 reduces to 2/3. The 384 reduces with the 3. 3 goes into that 128 times, which is 2 to the 7th times 2 is 2 to the 8th. And so that's just 2 to the 4th when you square root it, right? So 16 for x. And then you can get y by going back to our equation for y. Here's x equals the 16 right here, right? Then for y, we just go back to our equation for y in terms of x, which was y equals 384 over x. And so, yeah, y equals 384 over that 16. And I already found out that 384 is 128 times 3. 128 is 2 to the 7th. 16 is 2 to the 4th. Divide, and you get 2 to the 3rd, which is 8. 8 times 3 is 24. So y is 24. And those are the x and y values for that critical point for the area function. It's the only critical point. It's got to be the one that we want. If you want to do like a sign chart on A prime, you can, to prove that A prime changes from negative to positive at that x value, which means that that would be a minimum area value for the whole poster. You could absolutely do that, depending on what's required for your class. But for me, I kind of feel like, if we can tell that it has to be the minimum based on logic, I think that's good enough. So unless it says justify, then if it says justify, maybe you need to, like I said, prove that it's a minimum. Anyway, so now we're just interpreting the optimal printed area, because that's what x and y were. They were the dimensions, the way we defined them above. They were the dimensions of the printable region. So it's 16 by 24. And then if you go back up and just kind of interpret now, because the question said, find the dimensions of the actual poster, the whole poster, with the smallest poster area, right? And so now you have to add the 4 and 4. So 8 onto x, and the 6 and 6. So 12 onto y. And so 16 by 24 for printable becomes 16 plus 8 is 24. By 24 plus 12 is 36 for the entire poster. So the whole poster has to be 24 centimeters by 36 centimeters. And it has to be at least that big in area in order to have those margins and that printed region. That's it.